Welcome back to week 6, and here is another, yet another example from Dr. Selmer's book. It is notes to accompany this class. So we have an 8-pound weight. Oops, that's the next one. The weight of 8 pounds, and it's suspended by a spring that has a constant of 25 pounds per inch, which corresponds to 300 pounds per foot. The system is undamped, but the mass is subjected to a harmonic frequency of 7 hertz. So FF is 7 hertz, resulting in a forced motion amplitude, XM, equal to 1.59 inches. We want to determine the maximum value of the impressed force, right? So we want to find PO with the lettering that we're using right now. So we can do a little bit of conversion here, and we could turn this into feet. That's a good place to start. And we can also get omega F by multiplying by 2 pi, dividing it by 60. We get this into, where'd you do it? 43.98 radians per second. Good. And as always, if you're doing a vibration problem and you're given the weight or the mass and the stiffness, you can find what the natural frequency is going to be. In US units, we have to be a little bit careful. We have to go, K over M, but our M is not equal to 8 pounds. We want the M to be slugs. So we take our K, 25 pounds. I'll do the units again because it's worth remembering. Divide by 8 pounds. But you need to divide that by 32.2. So multiply up at the top by 32.2 feet per second squared. You will find that the pounds cancel out and the feet cancel out, and now you just have the square root of 1 over a second squared. So you know that must be, when taken squared, it must be per second, which is fine. That's the form that we want. So we have 34.75 radians per second, and we want to compare that. So we take an R. We don't write it in orange enough. Well, maybe we shouldn't. All right, so here's the ratio of the forcing frequency to natural frequency. We have 43.98 divided by our natural frequency, 34.75, and we have a 1.266 ratio. So we could look that up. 1.66 ratio. So here's 1.5, here's 1.6, here's 1.7. So we're somewhere in there. Right in there. Looks to me like we have an amplification factor that's kind of right around, so it's 0.2, 0.4, 0.6, right around 0.6. So what we can expect, but we actually have equations, so we don't have to just rely on that graph. So don't. Here's the equation that we will generally use for this. I keep accidentally writing M instead of O instead in there. So the PO that we're trying to find is going to be equal to XM times K times 1 minus R. Did I do this wrong? Shoot. Yeah, no, I wrote it wrong on my page. That's all. So that's just going to be equal to 0.1325 times 300 times 1 minus 1.266 squared. What we end up finding, it's going to be a negative number, but it doesn't really matter that it's negative. And then it's going to ask me Ask me, why doesn't it matter that it's negative? Because we're going to have a reaction here that looks like this right here, right? It's always going to be positive and negative. It's going to keep going back up and forth and back up and forth, back between a zero. So it doesn't matter that our answer is negative, because that's also going to be the same value when it's positive. You know, when it's going to cycle back and forth. So that's my explanation for it. So it's unnecessary to correct and say, well, it should be the absolute value of that. Okay, well, yes, but also it's going to be vibrating back and forth. We will do one more example for what would have been the class that I guess we already had on Wednesday, and then I'll break into the stuff that's going to be on Monday, which is actually tomorrow in several hours.